Object localization in remote sensing is a notoriously difficult problem. If you're trying to identify a specific building, a vehicle, or a natural feature from a satellite image, you usually face two major hurdles. First, the data is often degraded by atmospheric haze and low contrast. Second, building a specialized detection model typically requires massive, manually annotated datasets, which are incredibly expensive and time-consuming to produce. But what if we could achieve high-accuracy grounding without any task-specific training? Today, we're diving into a new hybrid pipeline called DiffuSAM. This approach combines the generative power of diffusion models with the precision of foundation segmentation models to perform zero-shot object grounding in remote sensing imagery. In recent benchmarks, this method showed a significant jump in performance, increasing localization accuracy by over 14% in certain scenarios compared to existing state-of-the-art methods. To understand how DiffuSAM works, we first have to address the quality of the input. Satellite imagery is rarely clean. You're dealing with pollution, humidity, and sensor limitations that create haze and reduce visibility. To fix this, the pipeline starts with a rigorous pre-processing stage. First, the image is converted from the standard RGB color space to the CIELAB color space. This is a critical step because it separates the luminance, the brightness, from the chromatic components. Once isolated, the pipeline applies contrast-limited adaptive histogram equalization, or CLAHE, to the luminance channel. Unlike standard histogram equalization, CLAHE operates on small regions of the image to enhance local contrast without overamplifying noise. After this, the image is converted back to RGB and passed through an unsharp masking operation to sharpen the edges. Simultaneously, the natural language query is processed. If you give a model a prompt like, "Find the blue car on the left," the conversational filler can actually confuse the grounding model. DiffuSAM uses Qwen-Image-Edit, a small language model, to rewrite the query, stripping away unnecessary instructions and leaving only the core descriptive elements. Now we get to the core of the system, diffusion-based localization. Instead of using a traditional detector, DiffuSAM employs Qwen-Image-Edit. This is a diffusion-based image editing model. The pipeline prompts the model to generate an edited version of the satellite image, where the target object is highlighted with a red bounding box. Essentially, the diffusion model acts as a coarse spatial guide, turning a text description into a visual cue without needing a single annotated remote sensing image for training. Once we have that edited image with a red box, it's passed to SAM3, the Segment Anything Model 3. SAM3 generates a segmentation mask constrained to that highlighted region, which converts the diffusion model's coarse cue into a structured spatial representation. But a coarse box isn't enough for high-precision work. This is where the adaptive refinement strategy comes in. First, the pipeline cleans the text prompt again, removing directional keywords like left or right. Since we've already cropped the image around the object, these spatial terms become ambiguous and can actually degrade performance. Then, the system makes a dynamic choice about which model to use for the final refinement, based on the size of the cropped region. If the cropped area is large, specifically if it occupies more than 10% of the original image, the pipeline uses RemoteSAM. RemoteSAM is specifically trained on satellite imagery and is much better at handling complex scenes with multiple objects and heavy background context. However, if the region is small, the pipeline switches to SAM3. In these cases, the initial localization is already quite precise, and SAM3's fine-grained segmentation capabilities are superior for pinpointing the exact boundaries of a small object. To ensure the system doesn't fail, there's a built-in fallback mechanism. If the primary selected model fails to produce a valid mask, the system automatically tries the alternative model. If both fail, it defaults back to the original bounding box generated by the diffusion model. So how does this actually perform? The researchers tested DiffuSAM on two major benchmarks, VRS Bench and NWPU VHR10. On VRS Bench, which uses oriented bounding boxes, DiffuSAM outperformed the current state-of-the-art, RemoteSAM, with a marginal increase in accuracy. But the real leap was seen on the NWPU VHR10 dataset. Here, DiffuSAM outperformed RemoteSAM by 14% in ACK at 0.5, meaning the intersection over union, or IOU, was greater than 0.5 in significantly more cases. Now it's not perfect. Because this relies on a generative diffusion model, there is a risk of hallucinations. If an object is missing or extremely difficult to find, the diffusion model might actually synthesize a fake object and draw a box around it. Additionally, because the initial diffusion boxes are axis-aligned, they can sometimes capture irrelevant neighboring objects, which can interfere with the final segmentation. Looking forward, the goal is to implement better controls on the diffusion process to eliminate these hallucinations and perhaps integrate generative models, specifically fine-tuned for remote sensing to further clear up atmospheric haze. By bridging the gap between generative diffusion and foundational segmentation, DiffuSAM proves that we can achieve high-precision object grounding in complex environments without the need for massive, task-specific training sets. It's a powerful glimpse into the future of zero-shot, remote sensing.